Okay, wow. So that is uh, potentially an exciting end to the contest. Um, so we're just going to wait a few minutes while we prepare to be able to reveal the result. So do stay tuned. There's many questions like, did someone solve question A? Because there's been a few attempts on it by the looks of things. Just a couple more minutes more and we'll hopefully get some results showing. Just a quick couple of minutes and hopefully we'll be able to bring you the results of the contest. Just doing a quick test. We should be ready hopefully soon to reveal the results of the contest. That was pretty exciting, and we will hopefully be showing, did anybody solve question A, for example? That would be pretty exciting. Just a couple more minutes and then hopefully we'll be able to do the results.
Okay, welcome to the results of UKIEPC 2020. We're going to start walking through the results pretty soon. We have a record number of teams because of the format this year, so we'll be going through a little bit more quickly than usual, and hopefully nobody feels like they're not getting their share of the limelight. Okay. Great. Max has told me my microphone is working, so here we go. We are coming up to "There's an imposter among us" who submitted right at the end of the contest. Was it all for nothing, or did they solve something? They solved something. Good. So the contest went well for one team at least. Moving up, Pointer. No, not Pointer. Napieralski. No. Continuing on. We've got a lot of attempts from this UKIEPC team. A lot of incorrect attempts. Sorry about that. Maybe we should draw less attention to these teams. One correct solution so far. So here we go. We live in the society, move up. GNZ, move up. Hexadecimal number moves up. Russell is not rustling. My team, good job me. UC LAN, no. Yep, another point for them. Hexadecimal is done. Go, 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 go. Yep. Society. Yeah, we're getting a lot of right solutions here. Great job, everyone. Then can one go up? Guru, no. Brunel, yes. Team 2 are done. Alpha Slav are going up. Cobra is going up. Darius staying there. Team 1 staying, and up. Go, go, go again. Going, going, going. Matthew Sermon. The Society boys are going up. Camille is staying. Team name. And MQ are staying there. These fan club is staying there. Alpha Slav are going up again. Manic Lad is staying. Good, we have some correct solutions still. Team Deadlocked is going up despite the name. Team Tiny Turtle is deadlocked. Team did this right, didn't do it right, they're staying. Whatever you pronounce that team as went up. Monk Marius is staying level 3. Lol goes up. Team 7 stays. Anan stay. Vitalis goes up. Smedjo stays there. Selena's team is going up. And Lincoln's one team is going up. Matthew is on a real winning streak here. Go, go, go is going up again. Alpha Slav is done for real now. Team 662 is not moving. Team Deadlocked team are staying there. Carrie Am is going up. Team Fox on the way up. Those guys are done now. Team Spaceship Operator is going up. Team Lol is staying there. Team Philikek is not moving. Darth Jar Jar is stuck. Segmentation Truth has escaped. Lincoln 2 are really done now, and Team Chocolate Boy are on the move. Team Worst Streep, Neighbours of Worst Streep go up. Matthew Johnson is still moving up. Ryan's in 1, has a lot of submissions. One of them's correct. Natural Born Coda, sorry. However you pronounce that team has gone up. Similar. The casters are staying there. Team 2 Pi are going up. Team Yes, yes. Team Some Guy, also yes. Team Moore is going up. Team 1 is staying. Team Go Go is going up. Team Fox have their last correct solution. Spaceship is stuck. Segmentation Truth is continuing to move. Team Chocolate is staying where it is. Mithrin Deer is not moving. None of these guys are really moving. Team 2 Pi, yep, 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 that was pleasant. Team Never, no, staying where they are. Team Hip Trees, going up. Shinny, yes, no, no. Team Tikva has gone up. I have a nagging voice reminding me that we have 100 more of these rows to go, and we're only through about 100 so far, so we're probably going to speed this up a bit. I apologize if I don't read out your name in an amusing or insulting manner. Will this ever end? Yes, it will. Okay, as we close in 50, we can start paying a little bit more attention again to the top teams. So, Team Right Shift up. Bad Treep, one of the Treep family, have gone up. In fact, everybody is going up right now. Blueberry joining. Patrick, well done. Vlad, good job. Team Nap, good. And Otosik is staying there. So 1 team on the way up. DSG213 moves up. I'm at Home moves up. Team Contest and Anonymous Squid are going up as well. Okay, George, good job, George. Cuckoo's Hash has moved up, and University of Manchester, which I think is just one person from University of Manchester, not the whole university, is staying in place 47, just in case at 46. Robertus staying at 45. But no pressure is going up. Okay, the Right Shift are staying at place 44, and Team Ananas are at 43. Bad Treep are keeping moving. Old Boy Squad the same. Patrick is occupying 42. Team Nap are not wanting to be in place 41, and that's going to 01 team. TSG213 keeping moving. Blueberry the same. Vlad the same. I'm at Home the same. And Anonymous Squid takes 40. Good job. Utah goes up. Cuckoo's Hash keep moving. George goes up. We have an unusually high number of solutions accepted per total submissions this year, which is pretty good. Team This Is Ray are taking place 38. Team Just As solved a problem. Daniel and Ye are solving problems. Polish Pigeons the same. Trinity Pigeons. Radoshden. Z. Yeah, Nucleus limit exceeded, not today. Simplex are the unlucky ones holding the bag there. Team OX4D, however, did solve that problem. Okay, Alexa has stuck on place 36 after a couple of wrong tries. Team Bad Treep are done with their submissions now. Take place 35. No Pressure Compete are still going though. 1,000,007 problems sticking on 34 for today. DSG213 isn't giving up. Vlad is and takes place 33. Old Boys Squad are also kind of retired at 32. Overflow done, 31. When all else failed, take a nap have finally dropped off. Blueberry the same. I'm at home is also perfectly happy at place 28. But Cuckoo's Hash are still going, and Utah are taking place 27. Team contest puts are on the move as well. Beta Cat solving problems. Everybody's solving problems. We might be here forever. Oh no, Team Z are on place 26, and that's where they're sticking. Daniel is not taking place 25, however. Team Kittens are doing that. Team Ye are taking 24. Radostin Chonev is taking 23. And the Trinity Pigeons are still solving problems. I believe that was problem K they flew up there with. So Team Brindza are taking place 22. Team Another Polish Pigeon still got some flight in them, and they solved problem K as well. Noodles Limit came stuck on problem L, which was one of the more difficult ones, and they are taking 21st place. We move up into the top 20. Frederick is not happy to be there. Team OX4D are perfectly happy to be place 20, and that's where they're staying. Bogdan has tried A, which had very few attempts, but had a bit more luck on problem E, I believe. So Basi 7000 and Hodderbox are on 19 and 18. No Pressure Compete, sticking at 17. DSG213 last submission, and it's correct on problem K. Cuckoo's Hash solved the elusive problem L. So Team Contest Plus, apologies for the wrong pronunciation earlier, taking place 16. Now, everybody is trying L from this point on from the looks of it, and George has got it. Daniel's got it. Justice hasn't got it. That's place 15 from Edinburgh. Stefan solved. Beta Cat solved. Wow, this problem is really easy. Another Polish Pigeon. Okay, not so easy. Place 14. Frederick has wisely decided not to try and solve it, and that's good for him. He's taking place 13. So Team Bananas giving up on problem A, but they made it on problem L, and so they're flying up there. And Bogdan similar. So it looks like we're just about done with problem L now. So from the top 10, we have George Shishirim, Daniel Ye, Team Beta Cat, Team Bananas. I apologize if I'm calling you a team and you're just one person, which you probably are. Team Stefan Konstantin Bulliger in place 6, the Trinity Pigeons or Pigeon in place 5, the individual contester in place 4, Team QWQ in place 3, and Bogdan Zidaru in place 2. And then we've got one more thing, this problem A, which Team DSG down on place 12 has solved. And they were the only one to solve it, which is really interesting. Usually that doesn't happen. So that concludes the results. And we're going to be moving to the solutions presentation pretty soon, so you can find out what was so difficult about A and L. And you're going to have to stay tuned for a minute or so for that if you're interested. If you're not, we're going to be putting all of the materials, test data, and solution slides up on the site in the next few hours as well. So thanks for that part, and I hope you enjoyed the fireworks, and we'll move on to the presentation slide in a second. Thanks.
Thank you to Robin for doing that. Soon we'll get some info about the solutions coming to you. Well done to those teams that solved A, and well done to the teams that won 2. That was very impressive. Of course, at some point, hopefully, we'll have NWork, the Northwest European contest. Still not quite sure how that is going to work yet. We haven't heard from them. We will be, it's being pushed to kind of springtime, and they will determine the rules for letting universities choose teams, as well as how they'll be ranked and so on. So we'll find out about that, and we'll broadcast information from our website just to help. But check nwerc.eu for information about NWork as it comes. I'll put that up as a banner, so you'll be able to see it. So I'm going to put Robin back in the stream. Welcome back, Robin.
Thank you, Max. Okay. So I'm going to assume everyone can hear me again. This kind of streaming with no audience is always confusing. But in the worst case, I'm just talking to myself and you're seeing the slides. So here we go. We're going to go through in alphabetical order through the problems, which means we're going to be looking at problem A, first of all, which was about sticking your finger in a shark tank, or rather a piranha tank, where fish will swim towards your finger for as long as your finger is exposed in the pond or pool. So the observation you need to make for this is that if you put your finger to the left of a fish n times and to the right of a fish m times, it's going to move n minus m steps to the left. So as soon as you know how many times you're going to put the finger down on one side, you can calculate the other side. And in fact, because the fish are arranged in a neat linear sequence, as fish usually are, you can get the entire solution just from that. So to get a candidate solution, you can just put 0 at the left and say you're not going to put your finger there at all. And you can go forward calculating the rest. And then when you have all of those numbers, some of which may be negative, some of which may be excessively high, you can just run through and find the minimum and subtract that from everything else. So that's going to guarantee that all of your numbers of pressures into the fish tank are non-negative. And that's all you need for the first stage. It doesn't guarantee that you can find a solution, because the solution that it implies may involve putting your finger in for too long and getting it bitten off, or it may involve trying to draw the fish right towards the edge of the pond, which isn't possible because your finger can't go that far past it. So with the solution worked out, we get to the hard part, which is proving whether the solution is correct or not, and whether we should output whether the case is possible. And to do that, we're going to need to simulate the entire run through of the solution. So some of you tried some fairly advanced ways of optimizing this, but in fact, you can show that the number of times you need, the number of seconds you need to put your finger into the tank for is small enough that you can just manage to simulate all of them one by one. The only thing you need to be careful of is making sure not to use too many fancy data structures or things like that to try and find the next place to put the finger, since that will increase your runtime. So in fact, you can just walk through from the left to the right of the tank, seeing if you can insert your finger at a given time, and if you can, putting it in for as long as either the fish next door or the solution you found constrain you. So you'll take the minimum of those two. And you know after that that maybe the previous place you could have put your finger now becomes available because you just expanded the region in which you can put your finger there by moving one of the fish on its border towards where your finger is now. So maybe you can take a step back, but you don't need to recalculate anything or run any kind of priority queue search or anything. You can just use amortized analysis to show that walking forward in the array until you find a place to put your finger and then taking one step back and continuing is perfectly optimal. So congratulations to the one of you out there that solved this. In the Benelux algorithm programming contest, where this was also set today, which was running in parallel with a similar problem set, it was solved twice. So that's across something on the order of 300, 400 teams. It's been solved 3 times in total so far. So next up, slightly easier in the grand scheme of things, still not the easiest question. And this one had a mistake in that we put one case in the data which had a number equal to 10 to the 18, which makes the problem a little bit harder for certain kinds of solutions written by a couple of people. But the overall question was, given a number with 18 digits at most, write it as a sum of less than or equal to 10 palindromic numbers. So the solution here is just to kind of dive into it and see how many digits can you eliminate with one palindrome. So if you have a number like this big one, 970894, etc. here, we're just going to look for the biggest palindrome that we can subtract and subtract it. And that should reduce the number enough that on the next iteration, you've got a much smaller version of the problem. And in fact, you can show that doing that 10 times is easily enough to solve the problem, as long as you take a little bit of care over the edge cases. You don't need to use 3 palindromes like the statement says. You don't even need to use 5, but there's a note here on how you can do that if that's the kind of thing you're into. So next up, in my opinion, still slightly easier than the other two, still not the easiest, problem about corrupted judge data in a programming contest, which we had great fun constructing the image for. In this problem, you have the time penalties from solutions, but you don't have the scores, and you want to find out, does this scoreboard actually make sense, and can you reconstruct it? So all you're going to do here is fill in the results in the most conservative way possible, not changing anything any more than you need to. And then by the end, you're going to try and see if this scoreboard is in any way modifiable so that it could give another valid scoreboard. So then you have a couple of edge cases as well, like the case with no problems solved. But in general, you just have to be very, very careful when solving this problem, and there isn't a lot of algorithms work for once. So next up, one of the more solved problems, possibly even the most solved problem. I think it had a solution within the first 2 minutes of the contest. Team in Dublin, I believe. So we have some money in various sacks as depicted here, and we're going to need to distribute it to 3 people, none of whom want to have less than the others. We need to find, can we do that equally? And this is sort of just a coding exercise. You just need to add up all the numbers and use your language's built-in operators to find the modulus modulo 3, to see if they're divisible by 3. And that's it. And then just print yes or no as applicable. So moving back up the difficulty scale, we have this problem called elevator pitch, where we need to serve as many, all of the slots in all of the floors in various buildings represented in a height map. And we need to find as few elevators as necessary to accomplish that. So we're just going to look at the tallest points first, because they're the most difficult. So we're going to take all of the points of all of the buildings, sort them by greatest height first, least height last, and then from each one, we're going to check if we already built an elevator there, fine, or an elevator that can reach to there, fine. If not, we're going to put an elevator there, and then we're going to calculate from there, where else could you reach in the building we're in, using a breadth-first search, which some of you may know as the flood fill algorithm. And then we're going to repeat that until we have nothing left to breadth-first search from. And the answer is just the number of breadth-first searches that we ran. So, next up, a problem that was solved fairly late in the game by quite a few teams. We have a graph. We have some shortest paths people are going to take, and we can optimize some of those shortest paths in terms of price by batching several up if they all go through the same points and paying a fixed rate per person. So the first thing we need to find is, for each person, what are the shortest paths they can take? And the easiest way to do that is backwards. You find from the endpoint, the idyllic village on node 1, if you were to take the shortest path to this node, which edges would you be allowed to use? Because that's going to be the same for every person traveling. So you compute that with a regular Dijkstra's algorithm run, and you save which edges are valid, which corresponds to if there's an edge between two nodes and one of them is distance x away and one of them is distance y away, then the distance of the edge should be x minus y. So knowing that, we have our set of edges, our subset of edges from the graph, which we can use to transport people towards the center. And we know everybody's distance from the center. So we know our base cost. And now we just need to find where to put our group ticket, which is going to end at the destination because that's always the best place, and start somewhere. So the first thing then for every node is to find which people are allowed to go through this node. And you can use a bit mask, which represents for each bit whether this person, person number I, is able to go through this node or not, is represented by bit I. So you're going to need 128-bit integer for that. And some languages come with that built in. Some of them it's an extension in the compiler. Some of them you just have to glue together two 64-bit numbers. Others you could probably even use something like a string. The advantage of that is that as you calculate which people can go to a node, you find all of the edges coming into it, which are on the set of shortest paths, and you just OR its bit mask with the node coming in. So if you have a node containing person X, and one of the shortest path nodes edges goes to node A, then A's bit mask will get person X ORed into it, which means that you only need to do one OR operation per number of edges in the graph, which is a nice optimization. So then, knowing this, for each node, you can run through which people are available and how much you'd be saving if you cut their journey at that point for X people traveling a distance of Y and instead taking the group ticket, which is a relatively simple calculation at that point. The hard part is doing all of the setup. So next up, we have a question about power generation on an island where everybody lives on the edge of the island in a big cycle. So what we're going to do is represent this as a minimum spanning tree problem, where every node has to be connected to power. And so if we say that power is also represented as a vertex in this graph, then every vertex has to be connected to every other vertex. So we're just going to make an edge from this fake power vertex we're going to create to each city in the input. And the cost of that edge is just going to be the cost of installing a power generator at that point, which is given in the input. Every other edge is given in the input. And so you just take the minimum spanning tree of that graph, and you're pretty much done. And there are some well-known algorithms for that listed here. Next up, a question about a rude waiter who wants to get rid of some customers as quickly as possible. So all we have to do here is, given a list of lists of things, print out one of those lists of things. And in fact, that's kind of the entire solution. So you just have to code that up and you should be done. You can even stop reading the input halfway through if you want. And this is another one of the easiest problems in the set, which was widely solved. Next up, question I. We have a sort of broken sort function in that it can only sort half of the array at most. We can run it up to 3 times on any subset of the array we want. And by the end, it had better be sorted because that's the task. So we're going to kind of go through this salami slice style. We can observe that if you can sort half of the array, a subset of half of the array, you can use that to sort a quarter of the array by taking the first quarter of the array and the quarter of elements that should be in the first quarter of the array and sorting them. And in the end, the elements that should be in the first quarter will be in the first quarter. So then you can do that again with the second quarter, the exact same principle. And then you may be thinking that you have 1 step left and you have 2 quarters left to go. But that's not quite the same situation anymore, because you just need to sort all of the second half of the array and you'll be done. So that's how you do that. You sort the first quarter, the second quarter, and then everything else, and that just works out. Moving on. Question J, jigsaw, which was another one that I believe unfortunately had a mistake in it. The original version of this problem had a limit of 10 to the 18. The one that we actually put up in the PDF had an input limit of 10 to the 9. And 2 test cases were left in which had a limit of 10 to the 18, which were removed at some point in the contest, which I believe everybody noticed eventually. So the actual task was, given the numbers of corner pieces, edge pieces, and middle pieces, figure out whether they correspond to a rectangular jigsaw arranged roughly as shown in the picture of the ICPC balloons. So the first observation you have to make is, for a given size of jigsaw, there's a very simple formula for how many pieces you're going to need. And right away, you always are going to need 4 corner pieces, and the other 2 are a little bit more involved and correspond to a couple of bilinear functions. But the good thing is you have 2 of these functions, and so you can use them to make some simultaneous equations and plug them into your favorite simultaneous equation solving process, which for me is a pencil and paper, and use that to get a formula for what the width and height could be. Then you have to check if those are valid widths and height, because, for example, a width and height of 5.5 and 6.5 is pretty useless. So in the end, you just have to do some linear algebra for this one. Okay, next up, a harder task again, kleptocrat, which is about finding a shortest path using a metric, or rather not a metric, but a distance function, which is the exclusive OR of the values on the edges between nodes. So one fairly important thing is to think about what happens if you retrace your steps, or you walk in a loop and retrace your steps. If you retrace your steps that you've already taken, the net exclusive OR value of the cost is 0, because the exclusive OR of anything with itself is 0. But if you take a walk to a cycle and walk along that, and then walk back to where you came from, the cost is going to be the cost of the cycle, and you can just ignore walking to it. So essentially what you have then is a collection of cycles you can use. And you can kind of crunch this down into a system which you can use to kind of pull in individual bits of the graph to solve the problem. So end up with something called a basis, which you can just walk through any initial route and go through the items of this basis, looking for things which could optimize your solution. And then when you find something that can optimize your solution, you take the exclusive OR of that with the thing you have. And what you're looking for is to reduce the largest bit in your path cost. And then kind of rinse and repeat. Good. So next, one of the questions which was solved extensively towards the end of the contest, but not a lot at the start, because it was supposed to be the hardest, in fact. We were kind of surprised that question A got less attention than this one. So we have a couple of strings, essentially, which kind of boil down to missing characters or one of about 28 possible other characters. And you need to find, ignoring the missing values where appropriate, how many different places are there where these two strings could match. So the most useful observation, which you can take, is that if you look at how many missing characters match separately from how many non-missing characters match, you can simplify the problem quite a bit. Because if you don't have to deal with non-missing characters matching up with missing characters, then everything you have to do from that point on is going to be matching values with values and just seeing, is this exactly the same or not, as opposed to having this wildcard system where a question mark can match multiple things. So with the question marks, it's very simple because you can encode them as ones and zeros, because there are just two possible values, present or missing. And you can perform a what's called a convolution, which is a pairwise vector multiplication where every item is multiplied by every other item. And that gives you at index x the number of matching question marks at that particular offset between the two strings. So if you had shifted the second string along by 5 places, your value at item 5 is actually going to be the number of question marks matching. I think this slide is actually a little bit wrong because you have to encode -1 values as well to deal with 2 question marks overlapping at the same place versus 1 question mark overlapping with something that's not a question mark. So this slide will be updated, but that's the general principle. And then the slightly more challenging and more compute intensive part of the problem is, once you've found the number of question marks that you're going to use in this part of the solution, how many actual directions are matching? And you can kind of use the same principle, except rather than having just 2 values, missing and present, you have 28 possible values. In fact, 29 possible values, because one of them is not present. So the trick here is that you can encode a value between 1 and 128 as its binary representation, which takes a logarithm of its value number of bits. And so while that kind of breaks down being able to calculate the exact number of matches, because some binary representations will partially match with binary representations of other numbers, what it does let you calculate is do all of the bits of this array match all of the bits of this other array, excluding ones where bits are 0 due to being not present, for example. So when you're looking for a match, you can use the result of two convolutions, one on this simple 1-0 array, one on this more complicated logarithmic array. And you can use the result from the first convolution on the ones and zeros to find how many non-present values you need to deal with. And you can use that to work out how many bits should match in a in something that has that number of question marks and the right length string. And essentially, you do that by just finding the number of missing values and subtracting it from the length of the second string. And so now you know that you're looking for exactly that number times log k matching bits in the second convolution. And so if you can confirm those two things line up, then you have a valid match at that point, and you can add it to your answer. One thing that we were slightly expecting was that some solutions would use slow FFT algorithms, things like that. But in fact, that didn't seem to happen. Most solutions were either 100% correct or 100% wrong. And it turns out a lot of you have FFT in your TCR. Good thinking. So as I say, I think the slide content here is not 100% correct, and it will be updated when it goes on the site. Moving on to the last question, which was not the hardest either. We have 3 arrays. Take the median of each element in the arrays, which are all the same length. So really, this is an implementation question again. The task here for people who haven't coded a lot before is to save the 3 lists in memory, calculate, run a for each loop through all of the 3 arrays at once using an index, and sort the 3 elements at that index and print the one in the middle. And that's all you have to do there. So that concludes the presentation of solutions. I'm not sure if Max has any site director or contest director level statements to say at this point. But thank you all for participating. Sorry for the couple of issues in 2 of the problems with the data limits. And I hope to see all of you again, either virtually at Newark or in next year's UKIEPC. Thank you.
So well done, everybody. Good job. That's it for this year. Hope you enjoyed the contest, and we'll see some of you maybe at NWork and definitely next year. Thanks a lot, Robin, for going through everything too.
Just to add one thing, by the way, I have